Back. Today we're going to talk about polarity and intermolecular forces. So, a quick review. Remember that every single element has a electronegativity value. Here's the periodic table, and this periodic table shows the electronegativity value for every element. This is based on a scale from a famous chemist. But basically, what does this number mean? This electronegativity number means the likelihood that something wants to gain an electron. So as you can see, the halogens are very likely to want to gain electrons, which makes sense because if these gain one electron, they will become like a noble gas in their outer energy levels. Whereas the alkali metals and the alkaline earth metals have low electronegativity values, so they are likely to lose electrons. And we already know that from our unit on ionic compounds and ionic bonds. So what does this have to do with polarity? Well, let's go ahead and look at a scale that shows different types of bonds based on electronegativity differences. More or less in every molecule, if you look at the different elements and you get their electronegativity values from the periodic table or from some sort of chart, and you subtract those electronegativity values, you will come up with a number. That number tells you the likelihood of what type of bond it is, whether it is ionic, polar, or nonpolar. So, for example, let's go ahead and look at CO2. C, carbon, has an electronegativity value of 2.5. Oxygen has an electronegativity value of 3.5. So if you look at this bond right here between these two atoms, we take 3.5 minus 2.5, we come up with 1. And you could then get electronegativity value over here, which would be the same. So 1.0. We then go back to our chart, and we see that if it is in that range, that bond must be polar covalent. Now, you already know what an ionic bond is, but what exactly is polar covalent and nonpolar covalent? Well, these are covalent bonds, but it simply means that one side of the molecule will have slightly more of a charge than the other side in a polar covalent. In a nonpolar covalent, the electron charges are distributed equally in the molecule. So right here, CO2 has two polar covalent bonds. But to make things confusing, this entire molecule is actually non-polar. So a non-polar molecule can have polar covalent bonds, but as you can see, this is a linear shape, and the charge on this side of the molecule, it would be the same as the charge on this side. So this entire molecule is non-polar. Now, that leads us to the first intermolecular force that we are going to discuss. Let's look at our chart. There's three forces I want to talk about: dispersion forces, dipole-dipole, and hydrogen bonding. These are forces between molecules that keep molecules together. Intramolecular forces are inside of molecules. Notice how these intramolecular forces are very strong. This chart is basically saying it's going to take a lot more energy to break apart ionic bonds and covalent bonds. But have you ever wondered, if we have H2O, one molecule, and another H2O, what really keeps these together? Well, that is an intermolecular force. These keep molecules together. And they are also based on charges, but they are much weaker. So, let's talk about dispersion forces first. These are the weakest intermolecular forces, dispersion forces. Let's go ahead and look at this little diagram here. This shows us a nucleus. Notice how the electrons are in their orbitals around the nucleus, and this could also be a molecule. And at some times, the electrons might just sort of bulge out to one side. And keep in mind, electrons have a negative charge, so that means this side of the molecule will be slightly negative. This little Greek delta means negative charge. And then this side will be slightly positive. Okay, so let's say we have two of these floating around. If these electrons sort of bulge out to one side and create this charge, they will actually not bond together, but they will be attracted to each other. Now, as you can imagine, this dispersion force, which is what this is right here, is very weak because it's really dependent upon orbitals and electrons simply being in the right place in the right time. So it takes relatively little energy to break this bond. Let me go ahead and give you one quick example before we move on. If we look at the periodic table, dispersion forces often happen between halogens because these halogens are often diatomic in nature. In nature, you will find F2. So let's just pretend here's an F and an F, F2. Let's say there's another F2. Well, these are nonpolar molecules, meaning this side of this molecule has exactly the same charge as this side. So dispersion forces will happen in nonpolar molecules. At some point in time, the electrons might just sort of be over here, more electrons. And so then, at some point in time, the electrons might be over here. This is nonpolar, this is nonpolar. And then this dispersion force attracts these together. As you can imagine, if you have more electrons in a molecule, the dispersion force will actually be greater. It will have a higher energy level. It will require more energy to break it. So, as you go down the halogens, these chlorine, bromine, iodine, they have more electrons. So as you go down this group, F2 would be bonded to each other and it's going to be a gas. Chlorine is a little bit stronger bond, bromine's a little bit stronger, and iodine, say I2, here's an I2, and an I2 will have a little bit stronger bond between them. That actually affects the type of phase they are in. Sorry, let me get rid of this extra. For some reason I had two of these in here. Okay, so let's look at this chart. F2, Cl2, Br2, I2. These are all halogens. But as you go down this list here, they have more electrons in them. And what that means is it actually makes them bond together slightly stronger. So iodine, if you go out and find it in nature, is actually solid. Bromine, Br2, is a liquid. And these are gases. Because if you think about it, here's I2 and I2. This bond will be stronger, so they will be a solid. Br2 would be a little bit farther apart. There's a B, there's a B. And so that would be a liquid. And then these would be very far apart. These would be gases. So the type of force that intermolecular force that holds these molecules together can actually tell us what sort of phase it might be found in. And then here we actually have the boiling point. Notice the boiling point increases as you go down. So it doesn't take as much energy to break F2 apart. It takes more energy to break iodine apart. So if you actually found a chunk of iodine with all these I2s combined, it's going to take more energy to break that up. Okay, that was the first force, which would be dispersion. What about dipole-dipole? Dipole-dipole happens in molecules that actually have two separate polarities on them. So as we see this OF2, this part of this molecule is negative because fluorine has more electrons around it, whereas the oxygen is slightly positive This would be a polar molecule. It has a dipole. So that's one pole here, and this is one pole here. Notice we already did CO2. This is nonpolar because of the shape and the charges and how they're distributed. So we have nonpolar and we have polar. Nonpolar, this will be a dispersion force. Between polar molecules, it will be a dipole-dipole intermolecular force, which is slightly stronger. And that makes sense because if you think about it, these charges are greater than when these electrons sort of bulge out on here. So let's go ahead and look at this. I'm going to go ahead and just take this, and I will do a copy, and I'll do a paste. So really, it might end up to where it's sort of going to attract like this. You can see the negative to the positive, or it might attract like this. And then we'll have more of these, and they'll all attract together and form a shape. And this intermolecular force, this dipole-dipole force, is stronger than this. Let's go look at our chart. Well, and by the way, this is in kilojoules per mole, which is sort of how much energy you need to break these apart. We say that dipole is about 5 to 10 kilojoules per mole. Units are in kilojoules per mole. Okay, now let's go to something called hydrogen bonding. Well, hydrogen bonding only occurs between certain types of dipoles. And let's go ahead down here. So hydrogen bonding is sort of like a dipole force, because here we have water, H2O, and as you can see, water has a dipole. This part of water is a little bit more positive than this part of water, which is a little bit more negative. So this really is a polar molecule. So this is just like OF2. It is polar. Now the difference, though, is it has hydrogen in it. So let's go look at hydrogen bonds. Hydrogen bonds will occur between molecules with NH, OH, or FH bonds. Okay, well, as we notice, this has OH, and this is another OH. So this hydrogen is going to be attracted to this negative oxygen. So on a test or a quiz, you always know when it's a hydrogen bond if it's polar and it has any of these types of bonds in the molecule. So just remember, basically it has to be hydrogen and then nitrogen, oxygen, or fluorine. Which sometimes people kind of remember this by saying humph. But it has to be a specific type of bond. Nitrogen to hydrogen, oxygen to hydrogen, or fluorine to hydrogen. These bonds tend to be a little bit stronger. If we go back to our chart, we can see that it could be anywhere from 20 to even a little bit greater kilojoules per mole, which still is nowhere near these intramolecular forces over here. But it's going to take a little bit more energy to break water apart. Okay. I wanted to go back. I forgot to show you this picture. This is a dipole-dipole. So it shows you how it sort of, it's kind of like the hydrogen bond, the way these molecules connect. But it just takes a little bit less energy to break it apart. So, very quick review. Intermolecular forces are forces that keep molecules or atoms together. The three that we need to know are called dispersion forces, which occur when electrons just naturally shift in a non-polar molecule or atom. That's the key. It has to be non-polar. And normally you can figure out if something's non-polar by looking at the shape of it and seeing the symmetry of the molecule. The second type of force is dipole-dipole, which occurs in polar molecules. Polar molecules have a negative and a positive side. They are not evenly distributed, and you can normally tell this by the shape. Like this is a trigonal planar shape, whereas in a nonpolar they're normally linear, or It just depends on the shape, but the charges will always cancel each other out. Hydrogen bonding is sort of the same as dipole-dipole, but it is only between a hydrogen and certain other types of bonds. And as we can see, the energy increases to break those bonds apart. So that's a real quick introduction. I hope that helps you on a test. And as always, if you have any questions, let me know.